Alright guys, welcome back. So today we're going to revisit a topic that we discussed in the standard syllabus, acid-base equilibrium. However, we're going to do it with respect to calculations with weak acids and weak bases. So here's before we get into it, here's a list of, a table of strong acids and bases and weak acids. The ones in bold are ones that you should know about. So these, I'm sure you'll be familiar with it in the standard level syllabus, so I'm not going to go over too much. However, here's some weak acids. So hydrofluoric acid is one you're expected to know is weak. Ethanoic acid you're expected to know is weak. This you're expected to know is weak. And this you're expected to know is weak. Now, like from memory, you're not expected to know these Ka values, but the strength of them you're expected to know. Now, for calculations of weak acids, Ka is small, meaning it doesn't fully ionize. So, and in some cases, it hardly ionizes as well at all. So, therefore, to determine the pH of a weak acid solution, you have to be given a constant which is known as Ka, which is essentially the equilibrium constant. So, and then, sort of, you can use the same method that was applied in topic 6, or for the higher levels. You could use the you can use a similar sort of method to find the concentration. So here, I'm not going to go through a sample calculation, but here I'll just sort of go through this example here. You know that's sort of the equilibrium expression you want. That's the equilibrium that you want to consider. You know that concentration is 1 molar. That you assume is 0 molar, but here the idea is that we assume water is negligible in its H plus concentration, and when it gives into it, and then 0, 0, we can set up an ice chart. So here's the change, and then here we have Ka, solve for Ka, and we get that X is that, put minus log of that, which we get 4.23. And you could do a similar sort of thing with weak bases. You could generally go through the same process as we did in topic 616. No, 717. Whoops, not 616, 717. But you can use the same sort of process for weak acids and weak bases. You just have to do the one extra step of taking the negative log or the negative log and then taking 14 minus that to get the pH of a solution. If you're given a question relating to the relative strength of conjugates, for an acid-base conjugate pair, you're expected to know that Ka times Kb equals Kw. Now, what does that mean? It means that the strength of an acid is inversely proportional to its conjugate base. And the inverse is true, that the strength of a base is inversely proportional to the strength of its conjugate acid. Now, what does that mean in the real world? Now, that means that if you have an acid with some Ka, right? If you have a strong acid, which has a high Ka, then you know that its conjugate base is really weak. That you know that its conjugate base is weak. Now, there is some sort of tribulations with that. Since you know that for most strong acids, Ka is in like the range of, 1 billion or some extremely crazy number like that. Now, we know that the ion product constant, or Kw, is this number. So if this is 1 billion million, this number here, in order to have this hold true, is really fucking small. So for a strong acid, the conjugate base is so weak to the point it literally is nothing. And the inverse is true for a strong base. Its conjugate acid is so weak that it does nothing. Now, however, for weak acids and weak bases, this isn't always the case. Since Ka is very small here, and this is a very small number, this number here, although it's certainly smaller than Ka, it's certainly something to consider. It would be bigger than Kw, so it does have, important acid-base properties that we should consider. That's what I want you to take away from it. And then here's sort of, and then similarly to go with Ka, we have a constant quantity known as pK, which is the negative log of Ka. The easy way to do it is that when you raise something to a negative exponent, the larger it's 1 over 10 to that exponent. if you have a smaller number in the denominator, you get a larger number overall, and if you have a large number in the denominator of a fraction, you get a smaller number overall. And that's sort of the way I tend to work through those questions. If I'm given pKa, I just generally tend to convert it to Ka, and I just generally tend to work in Ka because it's easier for me. However, some people might prefer to work in pKa. It doesn't matter. Stick to one and stick with it. This I sort of talked about already. Now the last thing I want to touch on is the acidity of salt solutions. Now, the way you go about it is that basically some salts have acid-base properties. Now the way you go about determining those acid-base properties is you look at the solution reaction, and then you look at the ions individually and determine if they are conjugate species of each other. So, for example, here we have Na and Cl. This has no acid-base properties. This is the conjugate base of HCl, which is a strong acid. As we discussed before, the conjugate of a strong acid is is technically a weak base, but however, the base is so weak since Ka for a strong acid is really high to the point of having no effect on the solution. Now, what if we consider ammonium chloride, which dissociates into this? Cl minus, we already know from the previous part that it is not strong enough to affect the pH of the solution. However, this is a conjugate acid of a weak base, which is a weak acid, which we know the value of Kb would be much larger than Kw, and therefore we do have to consider the fact that it would contribute some H plus to the solution. Now, since it's a conjugate acid, since this is a conjugate acid, NH4 here, we conclude that the solution would be acidic. Lastly, last example here, let's go through ethanoate, sodium ethanoate. Here, this was explained in part here. This has no acid-base properties that we know of. This is the conjugate base of a carboxylic acid, which is a weak acid. And since this is a conjugate base, it is a stronger base than water and is therefore basic, since this is a conjugate base. This one is a little bit tricky here. Oh, I forgot to mention, I should probably quickly explain what a Lewis acid and a Lewis base is. It's just like a Lewis base is a electron pair donor, and a Lewis acid is an electron pair acceptor. That's it. That's all there is to it, essentially. But here, we would have to use Lewis acid-base theory to determine its acid-base properties. This right here, as we know from topic 3, this will tend to form complex ions with water, where water is the ligand, and since water is donating its electron pair, this right here is acting as a Lewis acid, and therefore it's acidic, since this acts as a Lewis acid. This Cl minus here, we already explained in part A, that the conjugate acid, this is HCl, which is strong, and the conjugate base is super weak to the point of basically being nothing. Now, this is an important topic for when we do titration curves, because this is important in determining where the equilibrium or the equivalence point is in terms of the pH scale, because it's not always 7. So, with that, I'm going to end the video here. Thank you for watching.